Interference. Interference. To understand interference, first let us consider two waves coming from two sources. Consider two wave trains coming from two sources. When these two waves meet at a point, when these two waves meet at a point in space, we call them superimposition. Superimposition of the two waves. Then when superimposition takes place, the redistribution of energy takes place. Let us consider two special cases of redistribution. When the waves arrive in space, they create displacement. If the displacements produced by both the waves are in the same direction, here wave 1, wave 2 are producing displacements y1 and y2. If y1 and y2 are produced in the same direction, then the resultant displacement y will be equal to sum of these two displacements y1 plus y2. Such a superimposition is called constructive interference. Constructive interference. When the two waves meet, if the displacements produced by the two waves are in the opposite direction, then we say destructive interference takes place. Then the resultant displacement will be y1 difference y2, y1 minus y2. If the both are having the same frequency and constant phase difference and same amplitude, then the displacements produced y1 become equal to y2 and the resultant displacement becomes 0. Generally, such a displacement we call it as destructive interference. Generally, we take two waves of same amplitude and frequency in interference, and in destructive interference, the resultant amplitude is 0. The wave will be carrying energy. This energy will be distributed throughout the wave. But when constructive and destructive interference takes place, the energy will be transferred to the constructive interference position from destructive interference position. The energy will be distributed, it will be transferred. Such a process takes place during interference. That is why we say redistribution of energy due to the superimposition of two waves of same frequency and having constant phase difference is called as interference. So interference is defined as follows. Redistribution of energy due to the superimposition of two waves of same frequency and having constant phase difference is called as interference. Like this we define interference. Intensity at the point of interference. Intensity at the point of interference. To find the intensity at a point, first let us discuss about the interference at a point. Consider two wave trains traveling from the sources A and B. Suppose they meet at the point C in space. If y1 is the amplitude of the first wave, then the intensity of a wave will be proportional to the square of the amplitude. So the intensity carried by the intensity of the energy of the first wave is I1 will be proportional to y1 square. If the amplitude of the second wave is y2, then the intensity of the second wave I2 will be proportional to y2 square. If y is the resultant amplitude at C, then the resultant intensity I will be proportional to y square. So the intensity will be proportional to the square of the amplitude. But the resultant amplitude at C is y is equal to y1 plus y2, the sum of the amplitudes of the two waves. The distance travelled by the wave from A to C is AC. The distance travelled by the wave from B to C is BC. If we carefully notice, there is a small difference between these two distances. The difference in the distances travelled by the waves from the two sources is BC minus AC. The difference in the distance traveled by the two waves is BC minus AC. BC minus AC, this is indicated by delta L, and this is known as the path difference of the two waves. The path difference of the two waves means the difference in the distances traveled by the two waves. If delta L is the path difference and lambda is the wavelength of either wave, we are considering waves of same wavelength lambda. In such a case, the phase difference with which these two waves will meet is given by delta is equal to 2 pi by lambda into delta L. Phase difference delta is equal to 2 pi by lambda into delta L. Young's double slit experiment. In Young's double slit experiment, in front of a source, two slits will be placed very close to one another, and from these two slits at about 1 meter in distance, a white screen will be placed. On the screen we notice dark and bright lines known as bands. Generally we take monochromatic light like sodium light. So we notice dark and bright bands on the screen. Now this can be physically understood like this. The light waves are transverse waves. In transverse waves we know crests and troughs will be formed. So from the source, yes, crests and troughs will come out. The wave coming out will have crests and troughs. Let us represent crest by solid line and trough by a dotted line. So we notice from S solid line, dotted line, solid line, dotted line like this. Then the locus of the points which are in the same phase is known as wavefront. So I am considering a wavefront passing through the points, the slits AB. Passing through the slits AB, let us consider a wavefront. Both A and B will act as sources according to Huygens wave principle. According to Huygens wave principle, both the slits A and B will act as sources. That is, the wavefront which is incident on A, it will act as a source. The part of the wavefront which is incident on B will also act as a source. So from these two sources, once again waves will emerge. Now from source A, once again we notice the crest trough traveling towards right. From B also we notice crests and troughs traveling to the right, and these two waves get superimposed. When superimposition takes place, notice carefully that a crest is intercepting a crest is meeting a crest, a trough is meeting a trough, a crest is meeting a trough. Let us take three cases. When crest meets a crest, a solid line intersects with a solid line, it is the position of crest meeting a crest. If a dotted line intercepts with a dotted line, it is the point of constructive interference, a trough meeting a trough. If a solid line meets a dotted line, then it is the point of intersection of crest meeting a trough. When crest meets a crest or trough meets a trough, a bright band will be formed. If a crest meets a trough, a dark band will be formed. Consider the vertical line. Consider the vertical line which passes through 3 points. One is a crest meeting a trough, which is a dark band, a crest meeting a crest, a bright band, and then a crest meeting a trough, a dark band. So we notice bright and dark lines on the vertical screen placed. So this is how we have to understand the Young's double slit experiment. Let us derive a relation for the resultant intensity at any point P on the screen in Young's double slit experiment. Our aim is to determine the intensity at any point P on the screen. S is the source, AB are the slits, D is the distance between the two slits A and B, and PC is the screen placed at a distance D from the slits, at a perpendicular distance D from the slits. AP is the distance traversed by the wave from A, and BP is the distance traversed by the wave coming from B. So the path difference of these two waves is BE. If the corresponding phase difference is delta, then the two waves meet at P with a phase difference delta. Though the waves emanate simultaneously from A and B, they arrive at P with a phase difference delta. If A is the amplitude of both the waves, if A is the amplitude of the two waves coming from A and B, then we can write the relations for the two waves at the point P as y1 is equal to A sin omega t for the wave arriving at P from A. For the wave coming from B which arrives at P, the relation can be written as y2 is equal to A sin omega t plus delta, because this will have delta more phase than that of the first wave. Since the wave from B comes with a more phase delta, the relation for it can be written as y2 is equal to A sin omega t plus delta. We know that the resultant displacement is given by y is equal to y1 plus y2. The resultant displacement is given by y is equal to y1 plus y2. Let us suppose the intensity of each wave is I0. We know that the intensity is proportional to the square of the amplitude. So let us write the intensity of each wave as I0 is equal to Ka square, where K is any constant of proportionality. Now let us find the relation for the resultant amplitude y. Y is equal to y1 plus y2. Mathematically, y1 is A sin omega t and y2 is equal to A sin omega t plus delta. Hence, let us use trigonometric relations. From trigonometric relations, we will get y is equal to A sin omega t plus A sin omega t plus delta is equal to, that can be written as y is equal to A sin omega t plus A sin omega t plus delta is expanded. We know that it is equal to A sin omega t cos delta plus A cos omega t plus sin delta. After substituting the values of y1 and y2, let us take A sin omega t plus delta and expand it in terms of trigonometric relations. Then we will get the relation for A sin omega t plus delta as A sin omega t cos delta plus A cos omega t plus sin delta. So, by taking out A sin omega t common, we notice that y is equal to A into 1 plus cos delta into sin omega t, A into 1 plus cos delta into sin omega t plus A sin delta into cos omega t, A sin delta into cos omega t. Let us substitute. A into 1 plus cos delta is equal to r cos theta. A into 1 plus cos delta is equal to r cos theta, and A sin delta is equal to r sin theta. For A sin theta we substitute r sin theta, for A sin delta substitute r sin theta, and for A into 1 plus cos delta let us substitute r cos theta. Then the relation for y becomes y is equal to r cos theta sin omega t plus r sin theta cos omega t. R cos theta sin omega t plus r sin theta cos omega t, which can be written as, from trigonometry we can write this as y is equal to r sin omega t plus theta, r into sin omega t plus theta. This is the equation which indicates that the resultant wave is also simple harmonic wave with a phase difference theta. This equation indicates that the resultant wave is also a simple harmonic wave with a phase difference theta. Now let us find the amplitude of the resultant wave r. we have substituted A into 1 plus cos delta as r cos theta and A sin delta as r sin theta. From these two equations, our aim is to find the value of r. Squaring and adding, we get r square sin square theta plus r square cos square theta is equal to r square. So, from the two terms of the right hand side, r cos theta and r sin theta, when they are squared and added, we will get r square. So, we have to square and add the left hand side terms. So, r square is equal to a square into 1 plus cos delta whole square plus a square into sin delta whole square. A square into 1 plus cos delta whole square plus a square into sin square delta. So, r square is equal to a square into 1 plus 2 cos delta plus cos square delta plus a square sin square delta. That can be written as r square is equal to a square plus 2a square cos delta plus a square into cos square delta plus sin square delta. Cos square delta plus sin square delta is equal to 1. Hence, we can write this equation as r square is equal to 2a square plus 2a square cos delta. 2a square plus 2a square cos delta, that can be written as 2a square into 1 plus cos delta. But 1 plus cos delta is 2 cos square delta by 2. 1 plus cos delta is equal to 2 cos square delta by 2. Hence, r square is equal to 4a square cos square delta by 2. R square is equal to 4a square cos square delta by 2. This is the relation for the resultant intensity. Intensity of the resultant wave. We know that the intensity is proportional to the square of the amplitude. Hence, the intensity of the resultant wave I can be written as kr square. K is proportional to constant. But r square is 4a square cos square delta by 2. 4a square cos square delta by 2. Hence, I is equal to 4ka square cos square delta by 2. But I0 is equal to 4, I0 is equal to ka square. Ka square is I0. Therefore, I is equal to 4I0 cos square delta by 2. The resultant intensity I is equal to 4I0 cos square delta by 2. This is the relation that can be used for finding the resultant intensity at a point P. So, the intensity depends on the value of delta, which is the phase difference. The intensity will be maximum whenever this cos square delta by 2 becomes 1. That is, whenever delta is equal to 0, 2 pi, 4 pi, 6 pi, etc. Whenever the value of delta is 0, 2 pi, 4 pi, 6 pi, etc., the intensity is maximum. The value of maximum intensity I will be equal to 4I0. The value of maximum intensity I is equal to 4I0. That is 4 times the intensity of each wave. The intensity of the resultant wave is at maximum. It is 4 times the intensity of individual wave. I is minimum for values of delta, pi, 3 pi, 5 pi, etc. Whenever delta, the phase difference is pi, 3 pi, 5 pi, etc., the value of I is minimum. In fact, it is 0. The minimum value of intensity is 0. Hence, we can conclude that the energy is transferred from minimum to maximum. The maximum and minimum values indicate that the intensity at minimum has been transferred to the position of maximum. Intensity can also be expressed in terms of path difference. So far we have expressed in terms of phase difference, when the intensity will be maximum, when the intensity will be minimum, that is in terms of phase difference. Now I will explain in terms of the path difference, that is wavelength. The relation between path difference and phase difference is given by delta is equal to 2 pi by lambda into delta L. Delta L is path difference. For values of phase difference, delta is equal to 0, 2 pi, 4 pi, 6 pi. For values of delta 0, lambda is 0. If delta is 2 pi, lambda is equal to lambda. Delta L is equal to lambda. If delta is 4 pi, if delta phase difference is 4 pi, then the path difference delta L will be 2 lambda. So whenever delta is 0, 2 pi, 4 pi, 6 pi, then the delta L path difference is 0, lambda, 2 lambda, 3 lambda, etc. So the intensity is maximum whenever the path difference is 0, lambda, 2 lambda, 3 lambda, etc. Intensity maximum occurs whenever the path difference is 0, lambda, 2 lambda, 3 lambda, etc. If you take delta as pi, then path difference delta L is equal to lambda by 2. When phase difference delta is equal to 3 pi, then path difference delta L is equal to 3 lambda by 2. So whenever delta is equal to pi, 3 pi, 5 pi, etc., then the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2. So the intensity is minimum whenever the path difference is, lambda by 2, 3 lambda by 2, 5 lambda by 2, etc. So like this we will get maximum and minimum. So maximum occurs whenever path difference is lambda, 0, lambda, 2 lambda, etc. and minimum occurs whenever the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, etc. Graphical representation of intensity distribution. The intensity distribution can be understood by drawing a graph and representing it on the graph. Here I am representing the bright band with white and dark band with dull white, with dull color. Now the phase difference is plotted on x-axis. The phase difference is 0, pi, 3 pi, 5 pi, etc. to the right, and to the left minus pi, minus 3 pi, minus 5, etc. The intensity is taken on y-axis. The maximum intensity is 4I0, that is at the peak of this curve. The peak of the curve represents 4I0. Now whenever the phase difference is 0, we will get a bright band. So a bright line is situated at 0, 2 pi, 4 pi, etc. And a dark band is situated at pi, 3 pi, 5 pi, or minus pi, minus 3 pi, etc. So this is how we represent the intensity on a curve. We represent the intensity graphically. Applications of interference phenomenon. Interference phenomenon is used to determine the wavelength of monochromatic light, and the difference between the wavelengths of closely spaced spectral lines. If two spectral lines are very closely spaced, like LO1 and LO2, to find the difference of their wavelengths, we use interference phenomenon. We use this phenomenon to determine the thickness of a thin transparent material. We can find the thickness of hair. So materials of very thin thickness, they can be determined, their thickness can be determined using interference pattern. We can also determine the refractive index of a liquid or a gas. Using interference phenomenon, we can determine the refractive index of a liquid or a gas. We notice the flat surface in case of glass. It is also not as smooth as we think. to determine that flatness of the surface. To determine the flatness of surface, we use interference phenomenon. Light will be reflected from the surfaces of lenses and prisms. The reflectivity of the light from lenses and prisms can be determined using the phenomenon of interference.